Sample exam 7, question number 43. A ball is drawn at random from a box containing 10 balls numbered sequentially from 1 to 10. Let X be the number on the ball selected. Let R be the event that X has an even number. Let S be the event that X is greater than or equal to 6. And let T be the event that X is less than or equal to 4. Which of the following pairs, RS, RT, and ST, are independent? Question number 43, we're asked to find which of the following pairs are independent, and we're given 3 events, R, S, and T, and their respective probabilities are probability R is a half, probability of S is a half, probability of T is 2/5. So to test if they're independent is you have to find their joint probability of their joint distribution to see if it's equal to the product of their marginal distributions. So we'll just go through each of these. The probability of R and S, you can sort of rationalize it out. It's an even and has to be greater than 6. So 4, 8, and 10 are possibilities out of the 10. So it's 3 out of 10. And this can be rewritten as R times the probability of S given R, which is this, and that's what that equals. And that is not equal to the product of R and S, which is 1/4, not 1/10. So R and S are not independent. Probability of R and T, again, you can kind of rationalize it out that that's 2/10. Then this can be rewritten as R, probability R times the probability of T given R, which you can do the math and it's 1/2 in this, and that is equal to their marginal probabilities. So R and T are independent. Now the probability of S intersect T is 0. There's no way that you can be greater than 6 and less than 4, so it's 0, which is definitely not equal to the product of these marginal probabilities. So the answer is B. Number 44, let X denote the number of independent rolls on a fair die required to obtain the first 3. What is the probability that X is greater than or equal to 6? Number 44, we want to find the probability that X is greater than or equal to 6. Where X is the number of rolls it takes to roll your first 3. So we'll build this up in from beginning to end. The probability that we roll a 3 on any given roll is 1/6, and we'll call that P. That's sort of the probability of a success, or that we roll a 3. And so if we're going to let X equal the number of rolls for the first 3, and then let's look at an individual I. So the probability that X equals I. So this is saying, the probability that X is 100, meaning we roll a 3 on the 100th roll and that's our first 1. Or it could be 10, or any I. Well, if we roll a 3 on roll I, that means we didn't roll a 3 on the first I minus 1. So the probability that we don't roll an I on each roll, and each roll is independent, is 1 minus P, and there's I minus 1 of them. So this is the probability that we do not roll a 3 on the first I minus 1 rolls. And then this P is the probability that we roll a 3 on that ith roll. And then if we substitute numbers, 1 minus P is 5/6 raised to I minus 1, P is 1/6. So now to find the probability that X is greater than or equal to 6, we have to sum these probabilities from 6 to 100, because it could happen on any one of those. And now this we calculated as this, okay? Now 6, there's no index associated with it, so we can pull it out front, and then we expand this sum a little, which is this, and then this is a geometric series starting at 5/6 to the 5th. And so the formula for that is this. and that boils down to 5/6 to the 5th. Number 45, a random sample of size 5 is taken from a normal distribution with mean 0 and standard deviation 2. Find a constant k such that 0.05 is equal to the probability that the sum of the squares of the sample observations exceeds k. So problem number 45, I went through the answer and I thought, well, it's not 100% obvious the way I wrote it that it works. So I'm going to give a quick note, and I squeezed it in here before, after I wrote everything out. But if you take a data point, subtract the mean, divided by the standard deviation, assuming that x is normal, and we call that a zi, because the ith observation, that's a standard normal. And then if we square it, it becomes a chi-squared 1. Now, if we do that for each I, so we have the sum of these zi squareds, then it becomes a chi-squared with 5 degrees of freedom, because they're each independent and we're doing it 5 times, and it's chi-squared 5. So to find this probability, subtracting the mean of 0 and dividing by what ends up being the variance, which is 4, this becomes a chi-squared. So you divide both sides by 4. Again, this is a chi-squared. So you look in a chi-squared with 5 degrees of freedom, and we want this to be 0.05, which means this value is 11.07, which implies k is equal to 44.28. Number 46, let x be a continuous random variable with density function f of x given there. X greater than 0 or equal to 0, a and b greater than 0. What is the mode of x? Now, number 46, we're asked to find the mode, which means the highest point. So if we take this distribution and then find the derivative of it, it's going to find its local min and maxes. So the first derivative of this is this. You set it equal to 0. And I factor out this. And if it equals 0, that means this has to equal 0 or this has to equal 0. So you set them both equal to 0. X is equal to 0. And here you get x is equal to 2 over b. And if you plug this in, you get 0. If you plug this in, you get a positive number, so this is the mode, the maximum of that distribution. Number 47, let x be a random variable with finite variance. If y is equal to 15 minus x, then the correlation of x and x plus y times x is equal to number 47, we're asked to find the correlation of these two variables. Okay, and then the formula for that's the covariance of those divided by the variance of the first one times the variance of the second one, the square root of that. So to find these two values up here, so the covariance of this is equal to this, where I plug in, they give us y is equal to 15 minus x. So those x cancels, leaving just 15x. And the property of the covariance, you can pull that out front, and then it just becomes the variance of x. So now let's look at the variance of this second piece. So the variance of this, again substituting in for y, reducing it, so then it becomes the variance of 15x. The 15 comes out front squared, and we're just left with the variance of x, whatever that is. So the correlation between these two, the covariance divided by the square root of the variance, product of these variances, we'll just plug in the values, and then that's variance squared comes out as variance. That's 15 squared comes out as just 15. And it equals 1. And we should have known that because this is a linear, it's a linear function of each other. Number 48, Let X and Y have a bivariate normal distribution with mean of the X mean of 5 and the Y mean of 6. The standard deviation of X equal to 3, the standard deviation of Y equal to 2, and the covariance between X and Y equal to 2. Let cap phi denote the cumulative distribution function of a normal random variable with mean 0 and variance 1. What is the probability that 2x minus y is less than or equal to 5 in terms of phi? So number 48, we're asked to find this probability, and we know that x and y are normal, so any linear combination of x and y is normal, but we don't know the mean and the variance, so we have to find that. So the mean of this quantity, take the expected value, take it in, evaluate it, you get 4. The variance of this linear function here is you take out the 2 squared times variance of x, take out the minus 1 squared variance of y, 2 times a times b times the covariance, and these are all given, so it comes down to 32. So if this is a normal random variable, if we subtract the mean from both sides, and that's what this is, and divide both sides by the standard deviation, which is what this is, then this number boils down to 1 over radical 32, which in terms of this operator is 1 over square root of 32. Number 49, a random sample x1 through xn is taken from a distribution with density function f of x given there, x between 0 and 1 and theta greater than 0. What is the maximum likelihood estimator of theta? Number 49, we're asked to find the maximum likelihood estimator of this. First of all, we have to find the joint density of our data. That means take the product of each of the marginals, and we get this. So maximizing this would be pretty tough. So we take the log of it, and that's our log likelihood. So the n comes out front, log of that. Theta comes out front, log of this. Take the derivative. So we get 1 over this, times a constant, times chain rule, times the derivative of the inside, which is 1, so we get this. Derivative of theta is just the log of this. We set it equal to 0. And a quick solve, we get this, but it's not one of the answers. And so you have to know that the log of the product of numbers is the same as the sum of the log of those numbers. And then this is the answer. Number 50, a fair coin is tossed. If a head occurs, 1 die is rolled. If a tail occurs, 2 dice are rolled. Let y be the total on the die or dice. What is the expected value of y? Now, number 50, if you see or catch the trick, then it becomes easy or pretty quick. But if you don't, then it's a longer problem. So we're going to do it both ways, because on test day you never know which one you'll find. But if the problem becomes too long, there's probably a trick to it somewhere. So here the y is the outcome, and we get 1 through 12. D is the outcome of the die or dice if you're rolling 1 or 2. C is the outcome of the coin. And so to find the expected value of y, we have to find the probability of each of the possible values of y. And so this probability can be rewritten as this probability, where you're summing over all possible outcomes of the coin, and then you're using probability theory to rewrite it as this, Well, then this is just the sum of two observations, whether you roll or you flip a head or a tail. So this can be rewritten as, you know, the probability that we observe a head, and then it's the probability that the die sum to y given that we rolled a head, and then this is the probability we flip a tail, and this is the probability that we roll, that the two die equals this, you know, y given we flipped a tail. So notice that y is the outcome, you know, that we want, but that's equivalent to the, you know, the sum of the die or dice. And now we go through each possibility. So the probability that y is 1, that means we have to roll a head, flip a head, and we roll a die and it lands up a 1. I guess technically this is given that we flipped a head. And this is 1/2, 1/6, so it's 1/12. We'll go through a few of these and then I just give you the answer because I get tired of writing it out. So probably that y is 2 is, you remember we're going to use this notation here. So it's the probability that we flip a head, and then the probability that on the die we roll a 2, of course given that we flipped a head, and this is the probability we flip a tail, and this probability that it equals the sum of the two die is 2 given that we flipped a tail, which is 1/2, 1/6, 1/2, and 1/36, which is this. Now 3 is the probability that we flip a head, that we roll a 3, flip a tail, and the probability of that we get a 3. And there's two ways out of the 36, so that these add to 1/9, and then I just write them down. Probability that y is 4 is 1/8. I'm just going to do this. So here's all the probabilities. Now to find the mean, so the expected value of y is the sum of the possible values of y times the probability of observing that y. So we just plug it in. So when y is 1, the probability of a 1 is 1/12. When y is 2, the probability of y being 2 is 7/72. When we do that for all of them, probably y is a 12 is 1/72, and that boils down to 21/4. Okay, and this took a little time, not a crazy amount of time, but probably more than the standard problem should take. So clearly there's another way, but this is the route I went down first, so that's why I put this possible solution. Now here, if we look at these conditional expectations, so what's the expected value of y given that we flipped a head? So that means we're only going to roll one die, and the possible values are 1 through 6. So the expected value of that is 3.5, or 7/4. And here, if we flipped a tail, what's the expected value of y? Rolling 2 die, well that's 7. Okay, then if we find this, remember the conditional probability, so the expected value of y is equal to the conditional expectation of expected value of y given what we flipped, what coin we flipped. So those two are equal. So now the possible values for, and this is over, what coin we want, so over C in this case. And the possible values here are 3.5 and 7. But what's the probability that we observe this? And that's the probability that we flip ahead, which is 1/2. And here is the possible outcome of our expectation, which is 7. And what's the probability that we observe this value? And that's if we flip a tail, so it's 1/2. And then this boils down to the same thing, 21/4. And so it depends which method you use. This is, of course, much faster, but then you have to remember the conditional expectation. Anyway, I hope you enjoyed it. That's all I have. That's the end of exam 7. I have one more exam, exam 8, and I'm really getting tired of putting these solutions up there, but I am going to finish. If you like this video, please like it and subscribe so you don't miss the next one. Thanks. Bye.